Hello, welcome everyone. I'm going to present a work I have done with Jérôme Lebrun on the recreation of a power amp stage of tube guitar amplifier simulations for the web using Faust. So who are we? I am a professor researcher at the University Côte d'Azur, and I am the co-creator with other people, in particular with people who made Faust, of a web audio plugin standard, and a contributor to the Faust IDE. My colleague Jérôme Lebrun is a researcher at CNRS and specialized in signal processing in audio, and he has built several tube amplifiers in the past, and also some web audio plugins that we created are now commercialized by CNRS, in particular tube guitar amplifier simulators. And so you can see here a screenshot of some of our amplifier simulation in the Amped Studio digital audio workstation. We've been designing tube guitar amp sims in the browser since 2016. In particular, in 2017, we published and we got a Best Paper Award for the recreation of a Marshall GCM 800, and we recreated it using only pure web audio high-level nodes. That means the high-level part of the WebAudio API, and we did a 100% JavaScript implementation. And this worked pretty well. And of course, we relied on the C++ implementation of the API that was located in the browser. In 2018, we improved many parts of this work, and in particular, we designed what we called a guitar tube amplifier designer. This is the picture on the right, that allowed us to specify any topology for the internals of a tube amp, choose the parameters for different filters and so on. And we also created a much more accurate model for the tubes. That is one of the tricky parts. And also we, for the first time, we added a complete power amp stage simulation. And this recent year, we mainly focused on Faust implementations to improve many parts of this work. So quickly, let's look at the different stages that you can find on an amp. On a typical tube amp, you've got a preamplifier, a tone stack, and a power amp stage, and also some extra stages. So the preamp is the one you manipulate using the volume button. It will just increase the signal coming from your guitar that has a very low amplitude. And also it will sculpt it by traversing many tubes and filters and creating a first part of the final sound. Secondly, you've got a tone stack that is made of bass, middle, and treble filters. And finally, you've got the power amp that is controlled by the master volume and the presence knob, where the presence knob adjusts the brightness and sharpness of the sound in the power amp stage, and the master volume drives the power amp. It's the amount of amplification you will get by the tubes located in the power amp stage. You can get extra stages like reverb, tremolo, vibrato, equalizer in some amplifiers, but it's out of the scope of this presentation. So if we look at the back of a typical amp head, you will find tubes, and the tubes are full of non-linearity and also have a temporal behavior that is non-linear. So this is why usually it's one of the most difficult parts to emulate, to simulate correctly. And of course, you've got the speaker, and for this we are just using impulses, cabinet impulses, and we won't talk about this today. So each of these stages contributes to the sound, to its warmness, color, dynamics, the way the amplifier will behave if you struck strongly the strings or softly, and so on. So what we did when we created this using web audio is that we first recreated every part of the schematic, and finally we connect every part using the connect method from each web audio individual node to recreate the schematic. It's not as easy as it sounds. For example, the tone stack has a set of filters that are imbricated, and it's not easy to emulate. because you cannot just connect in series or in parallel these filters. And the power amp stage includes the negative feedback loop that is also a tricky part that we will detail a little bit later. So let me show you first a demonstration of what we did using pure JavaScript. So this is the amp designer. So we can play some sample. And you can hear the results. So I can change some presets here. So we can change the type of the tubes. We can adjust many internals, and this is the power amp stage at the bottom. This is the presence filter that is modelized as a bank of filters, and we've got also different parameters. So the end user will have much less knobs and options. It will be easy to use, and when we created this designer, we made some stress tests, and for example, we managed to run 15 simulations in parallel on a MacBook Pro 4 years ago, with no glitches and a CPU usage of less than 50% in a online DAO. So we had also to deal with web audio limitations. One of the main limitations is that every node that processes the sound in web audio process them using quantums, that means blocks of 128 samples. So every quantums at 44,100 kilohertz is about 3 milliseconds. And there is also some bugs and inconsistency between browser implementations. For example, Chrome adds a 3 millisecond delay by default behind the hood in any loops, while other browsers don't. So that means that the behavior, if you implement a loop in the graph, won't be the same in Chrome and in other browsers. So we reported the bug 3 years ago. It hasn't been fixed yet. And until recently, it was not possible to do stream processing at the sample-wise level without introducing glitches. So now it's possible thanks to the audio worklets node that has been added and that is available since this month in all major browsers. But for a long time, not being able to perform processing with time granularity below 3 milliseconds caused a lot of issues in the implementations of loops in the graph, the web audio graph, and in particular in the power amp stage. So the power amp stage is typically located in the signal chain before the speaker, before the end of the chain, and the schematic below shows that it contains a feedback loop. Actually, we called it a negative feedback loop because these loops re-inject the signal from the output, invert it only a few parts, so it has a negative gain. For example, it will just re-inject 40% of the outgoing signal, and it also adds a control over it in the sense of the presence filter. So you will re-inject to the incoming signal the output signal that is inverted with some frequencies that have been boosted or reduced. So this way, this negative loop enables us to have more control over what the power amp does. So in 2018, we managed to implement it even with the web audio constraints, but we had a very hard time fine-tuning all parameters, and the final result was quite unstable. So I can show a demo. If we tweak, for example, the value of the negative gain of the transfer function from the wave shaper that is located for emulating the tubes in the power amp, we can get some feedback effects that are hard to control. So let's look a little bit in details. So when you turn up the master volume knob, this means that you are augmenting the gain at the entrance, at the input of the power amp stage, and the signal gets more and more distorted because the tubes will be overloaded. The sound gets thicker and thicker, and this is how you can get fat sounds, high gain sounds, muddy sounds that you can find in classic rock or in metal, for example. So the presence filter is added to the negative feedback loop. It is a simple but efficient way for adjusting the brightness and sharpness of the sound. Usually it's a network of filters, and by turning the knob you are adjusting the gains of these filters. They are typically peaking filters. And the final result is very different to the one we can get with the classic bass, mid-range and treble knobs we have in the tone stack that merely equalize the output of the preamp. In this case, we've got a dynamic control. I mean, we are subtracting some part of the signal that is just targeting some particular frequencies. Let's talk now about the Faust reimplementation. So we had a good sounding amp simulation that has been tested by professional guitar player, was used in DAWs and so on. So the objective was to improve it using Faust, but we would like to reuse as much parameters that have been fine-tuned during these years as possible. So WebAudio used some filters from the API that had no direct equivalent in Faust. Also, the tube models we developed had to be ported to Faust. So the idea was also to get a power amp as customizable as the one we had. That means being able to tweak the value of the negative gain, control the feedback, adjust the set of filters from the presence, also the range of these filters and so on. So first step was to port WebAudio filters to Faust. So we spent some time experimenting with existing filters, and the behavior was different from the ones we had in WebAudio. So finally we had some help from Stefan Letz from the Faust team, who just ported the C++ code of WebAudio filters from Firefox to Faust, and he created the so-called WebAudio lib that is now available for everyone. So this way we were sure to have exactly the same filters with the same behavior. The tube models we had, we used to rely on wave shapers with transfer functions that we fine-tuned. We were also using some oversampling and some filters, because when the transfer functions are not symmetric, we have to rectify the signal. I'm not going to go into details. You've got references to the papers that detail this in the IFC20 paper. One part that is really tricky when you emulate tubes is their temporal behavior. If you strike slowly the string of your guitar, you won't have saturation. But if you strike them strongly, then the current coming to the tube will be higher, and the tube will start to get red and to get overloaded, and the signal will have some distortion. So for this we designed some wave shapers that can have their transfer function driven by the variation of the incoming signal. So let's look. So you see, so we had a tool that we could use for reshaping and controlling the way the transfer function will behave and will look. So let's start again. So this, when you are playing guitar and really striking the strings, gives a very, very responsive behavior. So with Faust, what we did is that we started first to look at the way Faust developers simulated tubes. So we looked at the guitarist project, for example. We also found some people who made VST plugins, but they created the DSP part using Faust code. So I'm talking about Oleg Kapitonov distortion plugin, or Nick Thompson from Creative Intent, who created a free plugin called Temper Distortion, and he provided the Faust code. But unfortunately, nearly all of these works used C and C++ tables for creating the transfer functions of the web shapers. The only one that had a 100% Faust implementation for the web shaper and transfer functions was the temper distortion plugin, and it also used a negative feedback loop that was different from the one we needed, but it was a very good starting point. And none of the work we looked at had an implementation of the sag and squish behavior. That means the dynamic variation of the transfer functions that could simulate the temporal behavior of the tubes when they are loaded and when they are just releasing the current. We managed to recreate exactly the feedback circuits and the schematic of the power amp we had with WebAudio, and we could run this in the Faust IDE. In the Faust IDE, and we even created the power amp as a plugin. We designed the user interface in the Faust IDE. Conclusion, you can see in the video that the differences in terms of sound timbre are small and subtle, and also we tried it by playing guitar real time, and we could not notice anything really annoying. On the contrary, it behaves well, it was more comfortable in terms of pleasure of playing, of dynamics responses. So we had to use also some tricks for simulating the temporal behavior of tubes, what I call the sag or the squish, the way the tubes are loaded and unloaded when you are playing a note, for example. So earlier we tweaked the transfer function in real time, depending on the envelope follower. So this time we used an envelope follower located in the signal chain just before the wave shaper, and instead of driving the transfer function, it drives the null pass filter. It was not, in my opinion, as good as what we had before, but it does the job. The Faust implementation was much more stable and versatile, so we could tweak the knobs, tweak the gain without getting into feedback. With the previous implementation, we could only tweak a little the parameters, otherwise the sound went into feedback loops very feedback effect very quickly. So the JavaScript implementation, remember, was based on blocks of 120x samples. So this introduced a delay of 3 milliseconds in the backfed signal, and really we didn't know exactly the overall effect of this thing. Our opinion is that it behaves a little bit like a comb filter in addition to what it should have done. This is why this was not correct in our point of view. So with Faust, we managed to do this much better, and the Faust IDE measurement tools helped a lot and proved the sample-wise nature of the processing. So we could see visually how the feedback loop was behaving, and we could check that this explained the increased stability of the loop. And the overall latency that we measured from guitar to speakers in the end was 3 milliseconds lower than what we had with the JavaScript implementation. So just to conclude, now we are redesigning completely a new AMP simulator that will rely on Faust for many parts. So the tone stack is redone in Faust, the power amp will be redone in Faust, but we might in the end have a full customizable AMP designer written in Faust. Thank you for listening.